Welcome back, everybody. Hope you had a great start of the week. And the topic this week, besides project number 1 and some messages concerning project number 1, is to continue our discussion of this gradient descent and then also this stochastic gradient descent method, which is going to be the method of choice when we are going to implement our own gradient optimization approaches in project number 2. So this is essentially going to be the topic today. And the hope is also to be able to start sneaking in our discussion of neural networks and the basic steps which pertain to the setup of a neural network code. And this is going to be the topic for the second project. Now, when we are getting close to the deadline for the first project, there is always a great desire for some more days. And I can never say no. So I guess none of you here, you want to have an extension, right? So we may actually, depending on input from people, because I've gotten mails from people where some of the groups have had problems because members have not participated fully, whether there could be an extension. If we do make an extension, it has to be fair for everybody. So if we make an extension, the possibility is that we could extend it till next week, till the next weekend, if that sounds okay with everybody. But then beyond that, we have to become a little bit mean in the sense that if you deliver later than the new extension, then we start subtracting points, typically 10 points per day delayed, unless you have an excuse for it. So would it be okay if we just make a small extension of the project? And then it seems everybody's nodding. I am, as I said, I've been agitating for procrastination. So this hits back to me when it comes to deadlines. And but the only thing then is that when it comes to next week, we will actually have to start discussing project number 2, because else we will be delayed with the startup of project 2. So those of you who are still a little bit delayed with project 1, you may be penalized with project 2 as well, then, with a later start. So I will send an email later today with a final date for the extension, if that is okay with everybody. Okay, so I wanted to, before we dive into the Jupyter notebook, because we're going to run codes and discuss these technicalities, I wanted to set up the basic algorithms for the methods which we're going to look at. And some of these algorithms are surprisingly simple. But then being surprisingly simple means that there will also be a set of parameters you can tune. So let's try to take a look and revisit what we discussed last week. Because last week, we spent most of the time on plain gradient descent, which means that we simply tuned the parameter, this so-called learning rate. Then we also introduced something which we call momentum, which I also like to call a memory-based parameter, where you can let the previous results weight the new results. And that can often lead to a better convergence, in particular if you have large fluctuations in your search for the optimal values. So the thing which we noticed when we run many of these calculations here is that everything which we do actually is based on us applying Newton's method. And we made a basic assumption when we Taylor expanded the objective function or the cost function, we stopped at the second derivative. And that was given in terms of the Hessian. And we ended up with an algorithm for the optimal parameters, which involved us being able to invert a matrix, which is defined by the second derivative of the objective function or the cost function. Now, that's the quantity we don't want to deal with, because it can be multidimensional. We also found that in case, unless we have a very simple function, we often end up with pretty complicated landscapes with many local minima, and that can obviously lead to poor performance. It's very sensitive to the initial condition, and it will depend on where you start your search. So when we deal with a method which is called stochastic gradient descent, we're actually going to split the data set in smaller blocks. And these blocks are normally called batches or mini batches. And that means that you will start your search in different regions of your data space. And hopefully that can avoid that you get stuck in a local minimum, because that's a condition which often can happen. Or you can be at a saddle point, which is even worse. Then the gradients are also computationally expensive to calculate. The cases we looked at last time were simple, this kind of simple vanilla cases where you had some few hundred data points. But in many cases, these gradients can actually involve huge data sets. And that's where this method of stochastic gradient descent, where you split the calculation of gradients into smaller subsets, that is faster to evaluate computationally than just dealing with a whole design matrix. So there are computational aspects where you often deal with other types of methods. So we can go on brute force, and we will see that in project number 2 and this first exercises we deal with, that it's pretty easy to set it up if we have a simple vanilla case with a polynomial fit, for instance. So these are the kind of problems which we often end up with. And it's very sensitive, as we saw, to this choice of learning rates. As we also saw last time, if you can calculate the Hessian matrix and calculate the eigenvalues of it, then you can actually get an estimate for what this learning rate should be. But normally you don't have it, which means that the results will be sensitive to that specific value. And many people in the calculations, they simply set up a grid of learning rate values, and they pick the one which gives you the best, for example, mean squared error. And it treats all directions in parameter space in a uniform way. And this is what we did last week. Now with methods like adaptive gradient, ADA-grad, root mean square propagation, RMS prop, that it's called, and ADAM, we're actually trying to bake in some direction dependence in this learning rate. So these are all methods, just keep that in mind, that these are all methods which try to circumvent you calculating a second derivative and then inverting that second derivative, which is written as a matrix. That's basically, everything now rotates around that. I should also say that this is a big debate in the community, and there are methods which are mathematically better than what we will present. And some of you may have heard of something which is called a Fisher gradient, something which is called natural gradients. These actually deal with ways of estimating the gradients by, or the second derivative, by approximating terms like the diagonals of the Hessian matrix. And these give often a better mathematical justification than many of the methods you will encounter now. Because after today's lectures, maybe you will have this kind of feeling of disappointment. Is this all that there is to it? Just me fixing some parameters and approximating some gradients? They do work, but there are better ways of doing it. And there's a lot of research in this field. Okay, so I wanted to quickly remind you of some of the things before we dive into the Jupyter Notebook for the rest of the day. So let's bring back the whiteboard and some of the technicalities which we discussed last week. So if you look at the problems which we had at hand, what we did was to take the Taylor expansion of the design matrix. And with the Taylor expansion of the design matrix, we stopped at the second derivative. And that's what we use to derive Newton's method. So what we ended up with was an iterative scheme, which went something like this. So these are the optimal parameters, and ideally, after n+1 iterations, this is given by some previous iteration. And then if we can calculate this quantity, so this is a Hessian matrix, which then depends on beta of n. And then this is multiplied with a gradient, which depends on this beta of n. So ideally, if we can do this and invert the matrix, we have essentially a recipe which we can move on with. And then we don't need to introduce this learning rate. So the learning rate was introduced by us, so that what we do now is actually something like this. And this can depend or not on a given iteration. And that's where these different methods come in. And these methods can be used irrespective of whether we do stochastic gradient descent or just a plain gradient descent. So we just need to separate these things. One thing is the way we treat the learning rate. And the other one is whether we do a stochastic gradient descent, where we will split the calculations in smaller portions, so-called mini batches. And then we would repeat these calculations many times, because calculating matrix multiplications and matrix vector multiplications requires a lot of floating point operations if we deal with the whole data set. If we can split these in smaller sets, that requires actually less floating point operations. And the other idea is that by us starting randomly in different positions in the data set with a random guess for our initial values, that may avoid us being trapped into local minima. So if you think of your data set, suppose now we have a one-dimensional case with an x and a y here, and our function looks something like this. So we could now start randomly with a specific guess for x, right? Our x is actually the beta value, so I should replace x with beta here. So this is a specific beta which we want to evaluate. And we would start typically here, if that is initial guess. So we start with a beta 0 and we place ourselves here. And that means that we will actually reach this point. And if we apply a gradient descent and reach that point, that is what we would call a local minima. We would rather like to be here. This is the point we want to reach. But when we have reached the local minima, then the gradient is actually 0, and we are stuck there. So gradient descent is normally sensitive to where we start the iterative process. That's one important aspect to think of. So we would call this one is a local minima. And the same here. This will be the global minimum. And this one is supposed to be flat. And this will be a saddle point. And as you have seen when you've been running Lasso, which implements a gradient descent actually with a constraint, then you probably gotten this message that it didn't converge according to the convergence criterion you had put up after a given number of iterations. So if you have few iterations, for instance, then it could happen that you would just be stuck. If you are in a saddle point, it could simply be that you get stuck here. So this will not be the kind of desired result you want to achieve. So placing yourself randomly in the space of these initial values for the search is something which is done by stochastic gradient descent. And the hope then is that by sampling stochastically through the whole space many times, you may reach a global minimum instead of a local minimum. Okay, so see, this is the kind of overarching picture, and why a stochastic gradient descent is normally favored compared to a gradient descent, where you would just start with a specific guess And maybe then you reach a minimum and then you're happy, but you may not have reached the correct minimum. And yeah. Yes. So we will have parameters. So the number of batches, how you split the data. So you calculate the smaller contributions of the gradient. And then, since what you're calculating then is an expectation value, you rerun this many times. And that defines a quantity which is called the number of epochs. So this is something which is defined in the field. So the batches is the way you subdivide and split the data. And you can split it as you want. And then you rerun it. So in principle, what you're doing is to calculate an average gradient. Does that make sense? So this is why you have stochastic gradient descent, because you're placing yourself randomly in the data set. Whereas when we run the cases last week, we simply started with the first data point and we run through it and calculated the whole gradient. But now we're not going to calculate the whole gradient. So let's, but before we do that, let's quickly remind ourselves of some of the technicalities here. Now, when you look at this problem here, this is an instance of a more general case. And the instance of the general case is us having a function which we call f of x, where x is a vector. And we could define this function as a half, since these are vectors and matrices. So we have a vector x multiplied with a matrix A, and then we have a vector x here. And then we have something like a b transposed times x. This is a function, a quadratic function in x. In our case, what we had was 1/2, and then we had the unknown parameters beta, multiplied with a Hessian matrix, the unknown parameter beta, minus the gradient, multiplied with beta. That's the function which we looked at when we made the Taylor expansion. Now, if you look at this general case, you can then, and let me find my notes here. I just need to find where I had my notes. I have an example here I wanted to show, and then yeah. So if you look at this function which we have here, this is the same as us when we take the derivative of this function with respect of one of the vectors x, and we want this to be 0. This is essentially what we have been doing. And this is the same then as a times x minus b. And that leads to one of these famous linear algebra problems, which you probably have seen many times, because b is now a known quantity. So this would simply be given by this linear algebra problem, which you probably have seen. Now, let me just give you an example here on the kind of functions which you could deal with. Suppose now you have a function which depends on two variables. So we have an f which depends on x1 and x2. And we could actually write this out now in terms of two vectors. So we would have an x1, x2, and then we take the transpose of it. And then we have a matrix, so I'm just putting in values in this matrix. And then I have the vector again, x1 and x2. And then I could have the vector b, which now in my case is given by 5. So as I told you, this is just an example I'm making up here. And then I have x1 and x2. This is just to illustrate what we actually end up doing. And then you can write it out. And we know that if we perform the multiplications, this is going to give us a function which goes like x squared, x1 squared, plus x1 times x2, plus 10 times x2 squared, minus 5 times x1, this is the last term, minus 3 times x2. So this is actually us rewriting a function which depends on two variables in terms of a matrix times a vector. This is nothing but that. And we are now doing that. The x's here are the parameters beta in our optimal fit. Does that make sense? Then, when we are calculating these gradients, what we actually are doing then is simply to calculate d of x1, x2 here with respect to x1, and we want that to be 0. And that gives an equation which simply says 2x1 plus x2 minus 5 of d of x1, x2 here, of d of x2 equal to 0, and that gives us x1 plus 20, x2 minus 3. And I'm not going to show you the solution of that one, because I guess you guys would get offended if I do that, because this is just two variables and we know how to solve that problem. But this is a useful example when you are setting up your own gradient descent. So if you're a little bit in doubt next week when you're setting it up, you could take this simple example and simply set up your first gradient descent calculation, because then you just have two gradients. So one is the first equation, and then you have the second one. And you know the answer. So typically what you would do then, you would set up something like an iteration here, where you would have x of I. So this x of I is either x1 or x2. And then you would have iteration n plus 1. And that would be given by xi in the previous iteration, minus, and now comes the gradient. So you would have a d of f of x1, x2 in our case, with respect to one of these. And then you would have a learning rate, which could now depend on the value of n, the number of iterations. Now in here, you would also evaluate that. So this would be f of x1 in iteration n and x2 in iteration n. So this is pretty simple to set up. And in case you worry that something may go wrong in your code, you can even set it up iteration by iteration, because you have a simple matrix and a simple gradient you can plug in and check. So I always recommend setting up some simple cases when you're developing something new. And this is a classical example you could use. And you know the answer. And then you could play around with different values for gamma and see how quickly you reach the exact result, or whether you just miss it totally, because you either have a too small gamma or you have a too large one. And in this particular case, what you see here is that this matrix which you see here, that is actually the Hessian, which we have. And it means that our x's which you have here, or this actually this b which you have, this plays the role of the gradient. But the Hessian matrix, which we have typically in this kind of optimization problems for machine learning, that is given by this simple example I have here. So this is a useful way actually to try to sort out essentially what we end up doing. And the approximation we made is that we Taylor expanded the cost function to second order, to the second derivative. Okay, any questions to this? Because what I want to do now is to set up some of the basic strategies for finding these learning rates and have an iterative approach to the learning rate so we can update it. So let's look at the approaches to the learning rate. So how do we set gamma? So there's a list of ways of doing that. And the simplest one is simply to keep a constant gamma. So let's just put it up. So we have a constant gamma, and we simply call it gamma 0 all the way. So this is not the best way of doing it. What you could do then next, you could let it decay exponentially. This is also one, many of these are just ad hoc recipes, and you would have to play around. So we would have an exponential decay, so we have a gamma of k. So this is iteration k, so let me put that as a superscript instead of a subscript. So we would have a gamma of k here, which is now given by some gamma 0, which is the initial parameter. And then we have the exponential decay part, where we have a parameter k, and we have a gamma here. And then we have a parameter tau, where these k, kappa, and gamma, and tau are parameters. And this parameter gamma k here, or this gamma, is often a gamma of iteration k minus 1. There is another function which is widely used. So we would have a gamma of k, which is given by a gamma 0, and that's the one I have implemented in the code here, plus a k times a gamma times a tau. And this gamma is not this tau, but gamma tau. So this gamma of tau and k and gamma 0 are parameters. Now new parameters. And they have to be set in one way or the other one. And a common choice is often that this gamma of tau is set to something like 1/100th of gamma 0. So you reduce it gradually as you move on. So you would start with a large value for gamma 0, and then you let it drop down gradually. And k is normally given by the number of iterations which you have here. So k is a number of iterations, and you would perform a given number of iterations here. So k is equal to the number of iterations. So this applies to both of these cases, and sometimes you can update it adaptively, or you simply have a k times a constant gamma tau. So if you go back to the equation which we had here, this could also be rewritten, and this is often done that. So minus k multiplied with this gamma of tau, where you have fixed this gamma tau, and you let k simply be the number of iterations. So there are many ways to update this. These are just some of the choices. Another choice which you may meet, or let me just keep this so you get time to write it. And you will see these implemented in many different codes. So you will have a linear one. And in that case, you would have a gamma k, which is 1 minus alpha of gamma 0 plus some alpha of this gamma of tau, which is roughly defined as before. And this alpha is then defined as k divided by tau. And then this is tau becomes a constant. So gamma of tau is a constant. Gamma 0 is a constant. And this gamma of tau is often set to be equal, again, something like 100 times gamma 0. And this other parameter alpha is also a new parameter. So alpha is a parameter. Which also needs to be set. So this reminds a little bit about this momentum approach, which we had last week, and which can be a way to speed up the iterative procedure when we are doing the gradient descent. And if you go into the literature, you will see many, many different ways of updating this learning rate. And this is irrespective of whether you do gradient descent or stochastic gradient descent. Now, the methods which we will, however, discuss, besides one of these simpler ones, is a method which is called ADAGRAD, which stands for adaptive gradient. We have this RMS prop. And then we have the final method, which is widely used, which is called ADA. And that's adaptive method with momentum. And they all have specific recipes. And normally what you would do in all these calculations is that you have to select, irrespective of method. So you can use this, or let me just keep it a little bit. So irrespective of the type of method, whether this is a stochastic gradient descent or a standard gradient descent, or irrespective of which one of you are using, you would always set up a grid of values of gamma 0, which you would start your calculations with. So that means that irrespective of whether you're using plain gradient descent So I'm going to use GD for that hereafter, or you're using a stochastic gradient descent, stochastic GD, and within these, or, and, any of the iterative updates in the previous page. So in my case, this is a previous page. So when you're going to look at the whiteboard notes, you will actually have to go one page back. So when I say irrespective of the iterative updates, with iterative updates, I actually mean these different ways which you see here. Okay? And you often, these are methods where you start with a value and it tries just to reduce it to a certain value. So that allows you, when you have set up, so irrespective of that, you would set up a grid of values. So you would have a gamma, and this could typically be something like, let's say 10 to the minus 5, you would have 10 to the minus 4, 10 to the minus 3, and you would very seldom go up to 1. So typically you would end with values like this. So every time you start your calculations, you could, one, just keep that value. So that means that all the gradients will be weighted with the same parameter in all their directions. The other alternative is that you have a reduction of the value gamma, which then takes an iterative update, and that can be done with the simple functions, the linear ones, the exponential ones, or we can use this different adaptive gradient methods. So let me also remind you of, since we now put up this type of equations, this second order polynomial in X, let me remind you of the kind of ideal which we would like to bake in. So there are methods like steepest gradient descent, which we discussed last week, which is different from the brute force gradient descent. So let me quickly remind you of that, because that expression for the update of this parameter gamma, that serves as a motivation for adaptive gradient, root mean square propagation, and ADAM. So let's look at the derivation of the steepest descent, which some of you may have seen. We discussed it last week. But let's look at that one as a kind of motivation for the expressions which are to come when we now look at the ADA-grad, root mean square propagation, and ADAM, which are the methods which we want you to implement at the end. So let's look at the mathematics of a simple method, which is called steepest descent, which is better than gradient descent. So this is just called steepest descent. And the way we derive these equations is actually starting with the way which we had with the second order polynomial in X. So let me just find my notes again. So what we have this function f of x, which is given by 1/2. And if it's a scalar, we don't need to care about the transposes. And then I'm just rewriting this as x transpose times b, and b is a known quantity and a is a known quantity, which in our case would be the gradient at a given iteration and the Hessian matrix at a given iteration. And x would be the same as our beta. So what we ended up with when we took the derivative here with respect to x, and we want to drive that to 0, that leads to a standard linear algebra problem, ax equal to b. And the way you solve this is by defining a residual, which I call for r. So this is my attempt at the letter r. And I define that as b minus a times x. And then I'm going to start with a guess. So the solution is obviously now when r is equal to 0. So this is what we want. Okay? That's pretty obvious. And we would start with a guess. Start with a guess. For x0. And this is actually the guess which we make for beta. So x plays the same role in these equations as beta, the optimal parameter which we're looking after. So in our case, this x0 is just a guess we make. And we would then have an r0, which would simply be given by minus ax0 plus b. And sometimes if I put x0 equal to 0, then this r0 is pretty simple. And that's a very common choice. So often that matrix A is a matrix which is positive definite, which means that this is a convex optimization problem. If that is the case, as we have seen in logistic regression and in linear regression, this is actually the case, then this is an iterative process which will converge to the exact solution irrespective of starting guess. But when we now let ourselves loose on neural networks, then life is not going to be that trivial because we have no idea whether the second derivative represents a matrix which can lead to a convex optimization problem. So if that matrix A, which we have, is a so-called positive definite matrix, you will get a solution in a given number iteration, which is the exact one, irrespective of guess. And that's a pretty nice thing. Okay, so the way you would do now is simply to continue like this, and you would have an rk, which you actually want to drive to 0. So you would have a b minus some a times an x of k. And hopefully after some number of iterations, what you have is a result, r of k plus 1, which is equal to 0. So if you now look at the x of k, we are also going now to assume that x of k plus 1 is now given by the previous value, x of k, plus some parameter alpha k multiplied with this r of k. So this is just a model which we make, or this is a general assumption we are making about the data. That means that I can rewrite this r of k plus 1 as a b minus a, and now I'm simply replacing r of k, and I can replace that one as an x of k plus alpha times r of k. So I'm just putting in, this is my expression for x of k plus 1 in my ith iteration. And I can rewrite this again as my b minus a times x of k which is actually my previous value, so my R of k, minus this alpha of k times A times R of k. So when it has converged, what we want this R of k plus 1 to be 0. So after a given number of iterations, we actually want to have this to be 0. That's the ideal we want. And when we do that, we can now actually, if we look at the equation which we have here, we can then simply rewrite that one, and then we will find an expression for this alpha of k. Because we have an R of k here, and then we have an R of k here. So what we get then, when we rewrite it, we simply get R of k is equal to alpha of k times A of R of k. Now, alpha is a scalar, but what you have here is an alpha, which can be a vector, and A is a matrix. So we would like to have everything as scalars. So I'm multiplying with Rk of Rk with this one. This becomes a scalar. And if I divide by Rk of T times A of Rk, then I can define a scalar, which is this alpha k. Then I can go back to the equations. And if I plug that in, this alpha, I actually have my update for x as I'm moving on. So this is the parameters which I'm looking after. So this plays the role of the learning rate. So this is my learning rate. This R of k plays the role of the gradient. And this A plays the role of the Hessian matrix. So the thing which is interesting for us now is that if I use steepest descent, and if I can evaluate this alpha of k, then I have the update for the learning rate. However, what you see here is that you need to have the gradient, this R of k, multiplied with the matrix A, and multiplied with this R of k again. And this is something you want to avoid. However, that expression, the steepest descent, is something which motivates these methods like ADA-grad, RMS prop, and ADA. So just keep this expression in mind here, because permutations or simplifications of that equation are what is used in the definition of these very effective ways of updating the learning rate. So if we want to summarize, and this is actually something which is really at the heart of all of machine learning, the way we deal with this learning rate in the optimization. And all these methods which you will hear about, they deal with finding some or the other way to keep information about the gradients so that you can get a better learning rate in the iterative process. I know I can see some kind of disappointments here, because is that really what is at the heart of machine learning? It actually is. So these optimization problems, you have to keep in mind that if we move away from the simple linear regression and logistic regression cases we've had till now, we are dealing with zillions of parameters. And then we have to make a compromise between the precision of the results and the number of floating point operations which we want to deal with. That is a kind of decision which you have to make. And then it's pretty common in all of these machine learning methods, you will see statements like, in the optimization of the problem for this data set, I used ADA-grad, which seemingly gave a better result than root mean square propagation. And in many cases, you don't know why that method worked better than the other one. Okay? So it means that when you run with neural networks, you have to experiment. So this kind of experimentation is part of the trade when you optimize a specific function for a specific data set. Any questions so far? I think, yeah. But steepest descent is slow because it normally acts in only one direction at a time. There is a method which is better if you can actually evaluate that quantity, which is called conjugate gradient descent, or just conjugate gradient method. And some of you may have heard of that. So that's mathematically the more efficient one. But the steepest descent is actually a step beyond the standard gradient descent, where you just have a constant learning rate. But the thing I want you to keep in mind, just so we stay with this kind of overarching message, is that irrespective of what you end up doing, you end up using one of these ways of updating the learning rate. And you have to try different ways. And all these softwares which you have access to, like scikit-learn, TensorFlow, PyTorch, and so on, they have these methods as options. Okay, so let's switch back to the Jupyter Notebook. But since we are just at the hour, I thought that we can take a small break, and then I'm going to put you all asleep with just slides after the break, without breaking the monotony. Okay, guys, let's take a small break. So in the slides here, or I'd rather say the Jupyter Notebook, what I want to do now is actually to go through several of these examples. So what we said, the kind of at the heart of all these optimizations, algorithms, what we are essentially doing is to find a way to update this learning rate in one way or the other one, whether we have a simple ad hoc recipe where we just keep it fixed, or we have some kind of exponential decaying where it just gets smaller. So you would start with a value like 10 to the minus 1, and then you make it smaller. And then you restart it with a new value, 10 to the minus 2, and you make it smaller. And then it just keeps going like this. And then you try to find the one which gives you the best mean squared error, to give you an example. And this is where we basically will be stuck with, how to say, the boundary conditions. And that's what we will have as input in the codes. So the other method which we discussed before the break, which we didn't say so much about, is actually this gradient descent. And if you look at many applications, there are large database sets, and then the training data can have an order of millions of examples. That means that if you were to calculate the full cost function or the mean squared error, if you want to, over the entire training set in order to perform only a single parameter update, that can become time consuming. And a very common approach, as it says here, to addressing these channels, the compute the gradient over batches of the training data. So one of the other hopes is that by doing that and placing yourself randomly, is that you can avoid being stuck in a local minimum. So there is the reduction of the number of floating point operations. And one of the reasons is that when you calculate the gradient, you perform a matrix times a vector multiplication many times. And if this is an n times n matrix, and the vector has length n, this typically requires n squared floating point operations. So if you have a matrix of dimensionality 10,000 times 10,000, you actually have a 10 to the 8 floating point operations. And if you have 10,000 parameters and you do hundreds of iterations, that quickly tells you how many times you're actually going to calculate these gradients. And that can really slow down performance. So if you reduce the data set you have when you calculate it, so you make these small batches, then the number of floating point operations required is smaller. So instead of a 10,000 times 10,000, you do this by 100 times 100, and that would be 10 to the 4th floating point operations. And then, since you then have reduced this in batches in smaller dimensionalities, it actually requires less floating point operations. Okay, so stochastic gradient descent, the way it functions, if you now think of the standard way you've been doing gradient descent, you now run over all the data points. And this is what you now want to avoid. In the previous examples which we had, we simply run in a slavish manner over all the data points and calculated the gradient. So what we do, on the other hand, is simply to calculate this gradient as a sum over a selected set of gradients. And in the stochastic gradient descent, what you typically do now is to split the data so that it has an amount of data m, and if your total number of data is little m divided by m, that gives you the number of batches. And it's common to call these mini batches or just batches, and then you would have a given number here. So if you have 10 points and you have 5 mini batches, that means that each mini batch has 2 data points. And then you would calculate the gradient just for each such data point. One of the hopes when you place yourself randomly in a data set and you do the search for the minimum, remember that when you do these optimizations, you're actually giving a start value for where you start your search. And by placing yourself randomly in the data set, the hope is that you can avoid being stuck in a local minimum. So the gradient step looks something like this as before, but now you have a sum over all these mini batches. So this would be your update of the parameter. And normally this k, which you see here, for one of the given ones which you have, would be picked at random with equal probability from 1 to n divided by m here. And an iteration of the number of mini batches is commonly referred as an epoch. And then you would just repeat this many times. So at the end, you are calculating an average of a gradient. So a simple code here would be you having 100 data points, you specify that one, so this becomes a parameter, and the number of epochs becomes a parameter. And what you will do then is to play around with these parameters. So in addition to your hyperparameter, like the learning rate and the lambda parameter you had in region lasso, you can add this penalization or shrinkage term to neural networks to any of the methods, irrespective of whether you did linear regression before or not. So you can set up a cost function for neural networks, which includes this hyperparameter. So then you have a hyperparameter, you will have the learning rate as a parameter, and when you do stochastic gradient descent, you have 2 additional parameters. Now, the important parameters when you're doing these searches will normally be this hyperparameter, which you have in, let's say, lasso and ridge, and the learning rate. These are often the parameters to which the data are most sensitive. But you need to play around with these parameters. So this is a typical way you would set it. And the question is, when do you stop? When do you stop the search for the minimum? So one possibility is actually to compute a full gradient after a given number of epochs and check if the norm of the gradient is smaller than some threshold and stop if true. However, the condition that the gradient is 0 is valid only also for local minima. So this would only tell us that we are close to a local or global minima. However, you could also evaluate the cost function at this function, store the result, and continue the search. And then if that test kicks in at a later stage, you can compare the values of the cost function and keep the beta that gave the lowest value. Many of the functions we've seen now are pretty easy to deal with. There is also another approach, is actually to let this learning rate or step length depend on the number of epochs in such a way that it becomes very small after a reasonable time, such that we do not move at all. And these are normally called scaling. And there's a lot of discussions on different scaling functions for the learning rate. And we presented some of them before the break. So you could have a constant, you could have an exponential decay. And one function which I implemented is one of these, which we discussed before the break, where you had parameters here. You have to specify this T0. And then as you move on, then this function for the learning rate gets updated. So it becomes smaller and smaller. So the way you would set it up here is typically to define some kind of change of the learning rate, whether it follows this function or an exponential one or the linear one, which we discussed. If you go into this link here, you will find many different types of learning rates. But normally we will not be using them. We will actually use either ADAM or ADA-grad or root mean square propagation. So I think in the literature, this kind of more fixed, simple recipes are basically being replaced by more efficient ways like ADAM and ADA-grad and root mean square propagation. So the code here gives you then the different parameters. So you would introduce more parameters. You would have a T0 and T1, and then you would let your gamma, which is the learning rate, change according to this recipe, which you see here. That's just the implementation of one of these methods. I wanted just to show you a code for this simple case we had last week, where we had this vanilla data with the X values. We have 100 of them. We have Y, which is just given by a first order polynomial. And then here I simply perform a standard linear regression, ordinary least squares, invert the matrix. I set up my design matrix. I invert it. I actually calculate the Hessian to find the optimal values for these parameters. And so this is just a repeat of what we did before. So I set up the gradients, and this would be, the first step would be the gradient descent in a brute force way with a fixed learning rate, or a learning rate which is now determined by the Hessian matrix, the eigenvalues, as we discussed last time. And the next one is my gradient descent with stochasticity. So you see now I have a number of batches, the number of data in the batches, and then the number of mini batches, M here. And then I do a random, find a random index. So that means that what I'm doing now, I'm calculating the gradient from this random index end, and I begin to the random index end, because it has a length of M here. So I'm calculating my X value and my Y value, and then I calculate the gradient here. And then I divide obviously by the number of points I have in that case. And this runs many times. So I take the averages over the number of epochs. And if I run this, so this would be the simple implementation of the stochastic gradient descent. And what you will see then is that the stochastic gradient descent is not giving you the exact value, but it will give you hopefully something which is close, because you're actually calculating this as an average of the gradients. And in that sense, what you see here is something which for this simple case is disappointing. And the problem, however, is that this is a too simple case, and you can actually run a full gradient descent here. But if you have a multi-dimensional problem, then these methods become superior, because the other ones will just use a lot of floating point operations to reach the same kind of result. So now you're calculating averages of gradients. And that means that there will be deviation from the small deviations from the true values. And this is why when you guys are actually setting up the codes for the next project, it's very useful to actually have tested your own gradient descent on some simpler cases. Because at the end, when you implement the back propagation algorithm, you have to be sure that your gradient descent or your stochastic gradient descent is something which functions correctly. So this is a simple implementation, but it contains the skeleton of what you would actually include in many of these applications. So in this code, we actually use replacement in setting up the mini batches. And if you follow the link here, there's a lot of discussion whether that is useful or not. So the thing which is nice or interesting with many of these machine learning methods is that there's still a lot of uncharted terrain, because many of these functions are often motivated in a very ad hoc or perhaps intuitive way, and they actually lack some of the mathematical foundation. Now, everything we have here can now be changed by including momentum. And as we saw last week, momentum, or this memory approach, is something which then can speed up the convergence. And what we did then was to actually add a new parameter, which we, so this is the same derivation which we discussed last week, but we would now have a parameter which now allows us to include information from the previous iteration. And then we have methods which we are coming back to a little bit later. So I'm going to switch back to the whiteboard a little bit later. But we have methods like this root mean square propagation, adaptive gradient, and ADAM. And I just wanted to discuss some of the codes first, and then go through the mathematics. Also, the mathematics between these methods is very nicely explained in the paper, in the book by Goodfellow, Benjo, and Courville in chapter 8. So I invite you to take a look at the algorithms, but I want to discuss the algorithms by looking at the codes. And this is, to a very large extent, what you will also end up doing. So I recommend to take a look at that chapter 8, because they actually discuss in detail root mean square propagation, adaptive gradient, which works very well for convex functions, and you will see that that often performs better than the other ones for the type of problems you've been looking at till now. And then we have the final one, which is ADAM. So when you look at practical tips in doing this, there is one thing you should do normally, which is commonly done, is actually to randomize the data when making mini batches. So because then otherwise the gradient descent method can fit spurious correlations resulting from the order in which the data is presented. Always useful to transform your inputs. That's something which we have been dealing with in project 1. You can look at the out of sample performance. Always monitor the performance of your model on a validation set, a smaller portion of the data, or the test set. And then the thing is that these adaptive methods, it's not always guaranteed that they give the best results. And that's why many people tend to use different methods, different adaptive methods for the same data set. And then you would typically land on conclusions that for this data set, ADA-grad did a better job than ADA, for instance. So there's no guarantee in the beginning that one of these methods will work best than the other ones. So you would have to play around. And this is sometimes a little bit both disappointing, and it takes time because you would then have to run over many different sets of parameters and methods. So we have the parameters, and then we also have the methods. And they all deal with ways of circumventing the problem of having to evaluate the second derivative. So there's another technicality I wanted to talk about, and this is something which is extremely useful, and it's about automatic differentiation. And we will discuss this in much more detail in the coming weeks, especially when we discuss neural networks and the codes for setting up a neural network. So adaptive or automatic differentiation, together with these methods, because ADA-grad and all the other methods, they actually deal with you calculating the gradients. When you have complicated functions, this is something you often don't want to encode explicitly. And then automatic differentiation is a tool which actually uses the chain rule on specific functions. And it's something which allows you to get derivatives to numerical precision. And we will discuss this in more detail next week and the week thereafter. But now I just wanted to mention to you how you can use it, because I will use it in some of the examples which follow here. So it's not symbolic differentiation, nor it's numerical differentiation, taking finite differences. It's actually you using repeatedly the chain rule and elementary functions. And by applying the chain rule repeatedly to these operations, you can actually obtain derivatives to almost numerical precision. So there are some examples. I wanted first to show you some examples here. So if you take this function here, you know what the derivative should look like. And here you would include automatic gradient, autograd, by simply running this. So AutoGrad is now a library which is not, how to say, updated, but you can still use it. The library which we recommend is called JAX, and I will show you examples of that later. But AutoGrad is a little bit simpler to use, and for somebody, sometimes it's not always that easy to have running on your laptops. It depends on distributions and so on, whereas AutoGrad has been well tested across distributions. So if you don't get JAX to function properly, you can use AutoGrad. And the examples here are examples which you would also write in the same way using JAX. And in this case here, we import the gradient calculation. So I define a function. I have my analytical gradient here, where I just punched in the equations. And then I have my functions I compute. This is the computed one, which is now given by this function fgrad here, where I simply use this functionality in automatic differentiation. And then I have the analytical one. And then I plot the analytical one and compare that with the one from the AutoGrad. And you can see that the difference between the two is 10 to the minus 15, which is 0. If you were to use finite differences, which is often the method you have seen in calculations of derivatives, you would never get this error. So we are coming back next week and the week thereafter to what happens in automatic differentiation. So now you can just think of this as a kind of a black box thing. So the gradient, this is another example. So this is a function here. I calculate the gradient. We know what the gradient should be here. So these are just simple examples. Evaluate the one has to be free. And then the analytical expression, we know that that is simply 3 times a squared, and that should be equal to 3. You can do this with more complicated functions, and you can then run this with a function which depends on x1 and x2 here, 2 parameters. You can give values to these parameters, and you can calculate the analytical gradient with respect to x1 and with respect to x2. And this is something which will be very useful if you go back to that simple function in terms of x1 and x2 I discussed before the break. So if you want the gradients, the way you would set it up here is simply to use AutoGrad, and then you have the gradient with respect to x1. You give this function f2, and you look at the first parameter, and then you have the other one which takes the second parameter. And in this specific case, you will also see that the calculations give you derivatives with respect to the different variables, which are just exactly the same as you would get by the analytical expressions. Now, I'm going to leave out some of these things because I will come back to it, but I wanted to discuss a little bit how to use this with ordinary least squares. So this is an example which you will find useful when you're setting up your own code. Yeah. I have defined NP as. Yeah, so it includes that in NumPy. Yeah, you can do that. You can do the same with JAX actually. So the if you run this code here, you have now a cost function, which is just your mean squared error. And I define x and y, the same stupid function which we had before. I calculate my parameter by linear regression, the standard algorithm, with taking the inverse of a matrix. I print this the values. I perform the standard gradient descent here with AutoGrad. And you can see now the training gradient is now given by grad, and I have the cost function. And now it's taking the derivative with just respect to one parameter here. And if I do that, you will see that I get the same as when I do the standard matrix inversion. So AutoGrad here, the only thing I did compared with the previous cases is that now I'm letting automatic differentiation, calculate my gradient. Whereas previously, if you go back to the example we had previously, I actually had to hard code the gradient. So the big difference now is that I don't hard code the gradient at all. And this makes coding much, much easier, much more user-friendly, and it saves you a lot of time because it's so easy to make small errors in setting up the gradient, especially if the function becomes more complicated. So I strongly recommend that you end up using these methods. And you can then repeat much of this with momentum. So this is the same gradient descent, but now with momentum. So if we now scroll down a little bit here, you would see now that I'm running this over 30 iterations. And I'm using momentum, which comes in here. And in that specific case, I have one calculation without the momentum. This is just plain one, but I use the gradient evaluated with automatic differentiation. And then I use my momentum method. And if I do that, I still need the gradient, which is plugged in here. But then I have the update, which now contains this parameter eta, multiplied with the momentum parameter, which keeps a track of the previous values, which I multiply with 0.3. And then I update my parameters, which are now given by new change. And then I save the change in terms of the new value. And then if you look at the gradients, which I'm printing here, you can now see this is just the own inversion. Now I'm chosen a learning rate, which is dictated by the Hessian matrix. And the first set here is actually my gradient from my own gradient descent without any momentum. And you see now after some 30 iterations, they're still not zero. And then I add momentum. And you see now with momentum, after the same number of iterations, I'm actually moving pretty down to gradients being pretty small. So you see here, it's at the third digit for both cases. So they're getting smaller and smaller. I need more iterations. Whereas here, without momentum, I have a gradient which is non-zero, and it still has a value at the second digit after the decimal point. So you see now the speed up by using momentum here has given me with 30 iterations actually an order of magnitude, a factor of 10 when it comes to the value of the gradients. And that is something you should implement when you're dealing with your own calculation of gradients. So momentum is very easy to implement. And you should have it in your codes. So take a look at these examples, because these examples which you see here, they contain also cases where we also implement stochastic gradient descent. Now, here, obviously, I have compared everything with a full implementation of Newton's method. So that means I take the same stuff, and now you see I calculate the gradient again using automatic differentiation. But now I calculate the inverse of the Hessian matrix, which is this quantity. So I don't have the learning rate. So the inverse, this specific case has only two parameters. So my Hessian matrix is a 2 by 2 matrix. And I'm simply inverting that one. And that's pretty straightforward. And the thing which is also particular for this specific method is that the Hessian matrix for linear regression is only your design matrix transposed times the design matrix. So that does not depend on the parameter beta. So I can invert that one irrespective of the iterations. Sorry for that. So this is why I calculate the inverse of the Hessian matrix here. And then I simply multiply with that one. So if I can invert the matrix, I should do that. And you see now, after basically one iteration, your gradients are 0. So nothing really beats the case where you can invert the Hessian matrix. So this is something you should think of when you make up your codes. If you have a few parameters, let's say on the order from 2-3 to 50, then to invert these matrices is actually pretty fast. And if you're doing linear regression, ordinary least squares, then your Hessian matrix does not depend on the parameters beta. And then you can just invert it once and for all and use it. So remember that your second derivative for ordinary least squares is just and that does not depend on your parameters beta. If you're doing a logistic regression, it will depend on the parameters. So ordinary least squares is actually one of these easier cases. And then you can invert it immediately. So, and you see here, the results are basically just spot on what you would get with standard matrix inversion. These are extremely useful tests to make, to get acquainted with automatic differentiation and many of these other methods. Now, what you will find here is just a repeat of the same thing you saw above, but now with automatic differentiation and stochastic gradient descent. So there is nothing particular new here, except that we include now down here a stochastic gradient descent, but where we have a learning rate, which is now changed according to this schedule, which you see here, which is just a kind of ad hoc scheme. But now again, we are setting up things in batches, and we are running over the epochs in order to calculate the gradients. And if we run that code, you would now see that this the Hessian matrix is now still a matrix which has not a very large difference between the two eigenvalues. This is my own gradient descent, which gives the same as matrix inversion. I take now my own stochastic gradient descent, and with this specific case here, I'm actually pretty close to the exact result with a stochastic gradient descent. But these are simple codes. And I can repeat everything with momentum, which I normally recommend including. And the only difference now from the previous case is that we simply have a case with momentum. Also, when we now do stochastic gradient descent. So keep in mind that all of these methods, the way we implement adaptive gradient, momentum, they can be applied to stochastic gradient descent or plane gradient descent. And what you will see here is me simply now doing this momentum update by including this parameter, which I call delta momentum here, which is 0.3. And then this normally speeds up actually the iterations. And you can see the quality of the results which you get. So the stochastic gradient descent for this similar case here is actually pretty easy to use and gives you decent results. Now, the next case here is actually with the adaptive gradient. So what I'm going to show you is actually how you can include information about the gradients and try to mimic something which could look similar like steepest descent, but it's not exactly the same because you don't end up calculating a vector times a matrix times a vector, but you're trying to mimic the adaptive procedure by including some information about the gradients. So again, you're probably pretty fed up with this simple example now. So I just switched to a polynomial of degree 2, just to make a change. A pretty advanced function, as you can see. And I have 1,000 data points. In this specific case now, I'm again using automatic differentiation to calculate the gradients. I define a given number of epochs, and I guess the number of unknown parameters. So I'm actually having I forgot to say that, there's always a guess on the values for the parameters beta. I have 3 parameters. And because I need 3 beta values, I have 1 for the intercept, 1 for x to the power 1, and then 1 for x to the power of 3. In this specific case now, I'm including a method which is called adaptive gradient. And in this specific method, what I'm doing now is first I calculate the gradients, and I'm using stochastic gradient descent. So I'm including the calculation of the gradient as before. So I could use this now to do a standard stochastic gradient descent. But now I'm calculating the gradient square. And this mimics a little bit to what you had in that denominator for steepest descent, because then I had the gradient times a matrix times the gradient. But now I'm not including that matrix. So I'm just setting up the gradient squared. And then I have the gradient here multiplied with my parameter eta. And then I divide by the square root of this gradient, which I have here, the gradient after a given iteration. And then I have a parameter delta to avoid cases where it could be zero. So this is actually the recipe for adaptive gradient. So instead of us now having the gradient times this parameter eta, what we are doing now is we're having an update where we actually divide by the square root of the, so we take the gradient squared and we take the square root of this quantity. And what do you get then, since we're also dealing with a convex function here to optimize, we're actually going to get something, even with a stochastic gradient descent, which gives us a result which is pretty close to the exact result. So adaptive gradient is a very powerful method, especially if you have convex functions you're optimizing. And the recipe which you see is something where you try to include information about the gradients. Then we have a root mean square propagation. And in the root mean square propagation, the recipe changes a little bit from adaptive gradient. And now we have an initial value for the learning rate. Typically, you would tune these initial values to have many different values. And you would run a value for the parameter rho here, which is now a parameter which enters this root mean square propagation. And let me just bring you back a little bit back in time here. So we have the equations for root mean square propagation, and they should be here. So in root mean square propagation, what you're doing now is you have an update on the gradients. So this is the gradient, GT, which you calculate. This contains an information from a previous result, S of t, that is, so it has a kind of momentum baked in information. And then it contains now the gradient squared. And then it has the learning rate, which we have here, the previous value. And then it has the gradient, but now divided by this quantity here, plus an epsilon, and you take the square root of it. So all these methods deal with different, almost ad hoc ways of updating the learning rates with information about the gradients. So that means that here now you have two additional parameters. So you're weighting the result from a previous iteration. And then you have a new parameter here where you simply include this parameter beta. So this beta controls the averaging time of the second moment and is typically taken to be about 0.9. So these are parameters which people would tune then. And the learning rate is typically chosen to be 10 to the minus 3, 10 to the minus 2, etc. And this epsilon is a small parameter which is simply included there to avoid that this S becomes 0. So keep in mind also that the multiplications and division is understood as an element-wise operation. So if we go back then to the code, so let's look at that one. So there are many codes examples here. Then this was a code we were looking at. In this specific case, now we're implementing this formula. So we have this parameter rho, which is normally put to some value 0.9 or 0.99. So this is again a parameter you would tune. And then you first calculate the gradients, and then you have this scaling. So you have the parameter rho and 1 minus rho times the gradient squared. And then the update now contains the gradient. And then this is divided by this square root of the gradient plus this parameter delta, which is included to avoid possible divisions by 0. And in this case, you see again, you have a result with a pretty similar quality. So these are methods which people often tend to use in all these kind of optimizations. And it's not given a priori which one gives the best result. But if you have a convex function, then ADA-grad is often the one which is used. And then finally, ADAM is a little bit, so this is an optimization with momentum. And in this particular case, we introduce a new parameter. And these are kind of canonical parameters which people have tuned in order to get good results on many, many different applications. So you would have you first calculate the gradients as before, and this is all done with a stochastic gradient descent. You calculate the gradient for that specific mini batch. You compute the first moment where you take this beta times the first moment, the previous value, and then you update it with the gradients. And then the second moment is now calculated with this new parameter, and you have an initial guess for the second moment. So you need to set initial guesses for these values, as you can see, for every epoch. So every epoch you repeat this. And then again, in this case, you have the gradient squared. And then the first term is actually us taking the first moment and divide by the beta 1 to the power of iterations. I don't remember exactly why it has the power of iterations. I have to look it up again. I always forget. And then the second term is actually pretty similar equations. And then the update is given by the eta parameter times the first term and then divided by the square root of the second term. And the theta value, which you would typically get from ADAM, are essentially better than the other methods. And you see now that this is really to 6, 7 leading digits. This gives you a optimal parameters, which are exactly what you would get from standard inversion. So these methods are methods which try to bake in some information about the gradients in different recipes. And everything here is done in order to circumvent, again, calculating this Hessian matrix and inverting that one. I plugged in some examples on how you can do this with logistic regression, so feel free to look at that. Now, presently, and we are going to look at more examples using JAX, is actually you can actually replace the standard derivatives which we looked at before with JAX, which stands for accelerated linear algebra. So it's AutoGrad and accelerated linear algebra. And that's essentially, it aims at much more efficient code for differentiation, vectorization, and parallelization. And it promises to actually, both include AutoGrad and also be able to vectorize and speed up your code. So I recommend, if you have time, to take a look at it, because we will use JAX in many of the examples which are coming. And here again, you would now have your cost function for the logistic regression. And in this specific case, you would calculate the derivative of that one with respect to this logistic regression function. Okay, so these examples which we are coming back to, I wanted to give you a survey of the different methods. And if you then go back into the textbook of Goodfellow et al., you will also see a description of all these three algorithms. So what I did now was to show you how you can encode what is in a textbook. So when you're going to apply these methods and look at the exercises, I recommend that you try to look at both the book and the codes which I put in here, because that hopefully will give you a more feeling of why it's encoded in this specific way. We are going to use these examples in the exercises next week and also in the build-up of project number 2. Coming back to project number 1, if it's okay for everybody, we're going to put a deadline till the end of next week. So people will have a little bit more time to wrap up things, if that is okay with everybody. But we will also start with the exercises for project number 2 next week. Because else we will, we will run out a little bit of time with different things we have to do with project number 2 here. And next week, we will actually start with neural networks and the mathematics of neural networks. And we're going to set up the algorithms for running a neural network. And deep learning methods are the methods we will cover for the rest of the semester and spend most of the time on these. Any questions? I know this is a technical session when it comes to these different methods, but these are the methods which are really at the heart of all of machine learning. And you see that making improvements here is something which is of great importance for basically all of the optimization we've been discussing. Okay, next week, we begin with neural networks, and that's a little bit more fun. Okay, guys. See you next time.